Chapter 7, Transverse Shear. Let's solve another example in Chapter 7, Transverse Shear in terms of nail spacing. This is an interesting problem which a, a box is consists of four identical boards which are connected, nailed together, and each nail has a capacity of 30 pounds. So each of these nails can stand 30 pounds shearing force, and also a vertical, and that's a cross section of a cantilever, hollowed cantilever beam which happen to handle a 80 pounds concentrated load at the top here. So you can see the effect of concentrated load, which is 80 pounds applied at the free end of concentrated load of the cantilever beam. And then we want to know what is the vertical distance, of vertical nails, and also distances between the horizontal nails at this cross section. Let's see how we can approach this problem. So if you look at the cross section here, that's again consists of four of these boards combined together, nailed together in a vertical and horizontal directions. So that's the horizontal nail. This is a vertical one. So for the centroid, the very beginning step of this problem is the centroid calculation, because our cross section is a symmetrical geometry. That's a centroid is stand at the center. There is no need to calculation of that. But for moment of inertia, so if again we do know the centroid is at the center, and I is, if you just consider a box, consists a solid box with the dimension of 6 plus 1.5, that's 7.5 inches. That's 112 base cube height. Base is 7.5, height is, that's a 112 7.5 to the fourth minus inner one. So that's 6.6 minus 1.1, and that's 4.5. And if you do so, it just gives you a negative 112 base cube height. Again, height and base are similar to each other, so that's a calculate the moment of inertia. It just gives you a moment of inertia equal to 229.5 inch to the force. As soon as we have the moment of inertia for calculating the Q, shear flow is VQ over I. So if we want to calculate the shear flow in this kind of problem, just for in case of vertical nails, just assume if we want to flip-flop this nail from the flip it 90 degrees from vertical horizontal direction to a vertical one, just assume that we can do this, we are allowed to do this. So it just says if we want to see the effect of a vertical nail, it just we can assume that we have two vertical nail, and just holding this A prime area from the rest. And if you want to separate it due to a stress induced by a bending moment, just assume we are pushing the top bar to the board, and these two nails stand against this force and want to keep the top board at its location. So it just like we just simulated like this. So if we just applying a pushing stress to the pushing force to the board, and the two nails they are against that, and that's a effect of a vertical nailing. These are vertical nailing. We just assume that we can flip these nails like a horizontal vertical condition, and in that case we can just go with total area at the top, that's a prime, and that's 7.5 one dimension and times the thickness of each of the boards, which is 1.5, and our q for this kind of shearing, that's a prime, y bar prime. Y bar prime is the distance of the centroid from here to the centroid of the entire area, and that's a 3 inches, and our area is 7.5 times 1.5. And if you calculate the first moment of area for this part for the top section, it just gives you a 33.75 inch cube. Likewise, if we want to see the effect of this time, we are working for horizontal nail or nails. So in this scenario, we can just assume we can just replace or flip-flop the vertical nail at this part, and just flip it like 90-degree. Just assume we can have this nail something like rotated by 90 degrees, and we have two force in two nail in horizontal. This is the real one. The other one can just replace it like that. So if we can this simulation, so it just says now we do have two horizontal nails and holding this much area. So you can simulate it like this. If we have again a push to the board and want to separate the top board, it just affects in this much area. So these two horizontal nails prevent the top board, but this amount of top board from moving or being separated from the sides. So in this scenario, if we want to calculate, again, this is our simulated and for our cross-sectional area. So in this part, our A prime is a 7.5 minus 1.5 at this part, and we are losing 1.5 from here. That's 7.5 minus 3, that's a 4.5, which you can see here, 4.5 times a thickness of each of the boards is again 1.5. So our cross-sectional area is, again, the centroid remains the same, our Q, this time it's going to be 20.25, that's inch cubed. Unit of first moment of area is cubed. That's 20.25 inch cubed in terms of first moment of area, this time for this amount of to the horizontal nails. And then if you want to calculate the shear flow at B for vertical condition, that's the formula is V shear force times Q at B, which is for vertical condition, over I. So V is provided, I be calculated, and QB is just replaced from the previous part, which is 33.75 inch cubed for a vertical situation, and that gives us 11.76 pound inches, and that QB is a 11.76 pound per inch, and for QC for horizontal condition, which we already calculate the QC, and shear flow, which is this is a lowercase a small q, that's VQC over I, and shear and moment of inertia remains the same. QC replaced from the previous step over here, and that gives us 7 point almost 1 pound per inch for a horizontal nailing. Then QC is calculated, shear flow is calculated in this scenario. So you can easily see what happened here. And if you want to compare the shear flow in the horizontal, in the vertical condition, comparison to horizontal nails, can easily, the formula is V over I times Q, and we already calculated QB is 11.76 and QC is 7.059, and definitely QB is higher, QB is higher than QC, and that's the only reason for that is B remains the same, I remains the same, and Q is A prime times Y bar prime. In our case, Y bar prime is also 3 inches, remains the same. Centroid from here to centroid of entire shape for both of them remain the same. The only difference is the area in horizontal condition. Area in horizontal condition is far bigger. This area in vertical nailing is far bigger than, or at least is something like bigger than the horizontal nailing condition. That's why we get a larger shear flow in terms of the vertical nailing in comparison to the horizontal one. And if we want to, at last, if we want to calculate the distance between vertical nails, which is SB, so we want to do that, that's the distance between vertical nails in cross section. So the formula is number of vertical nails times force of nail is equal to total shear times Q over I times S. Mhm. So for example, if we want to calculate that for vertical condition, that gives us Q in B, which is this part. And if you remember, you can just simulate it like this one, and it definitely shows us that the two of nailing, two vertical nails, they hold the top part, and so just replace the number of nail by 2 and times the capacity of each of them is equal to 80, which is the vertical force applied to the beam, cross section of the beam. You can simply replace QB here. I is for the entire section. The only unknown is SB, and SB, the distance of vertical nails is going to be 5.1. You can use a 5 inches for distances between vertical nailing. And that's at this distance. My bad. That's just as soon you have another vertical nail. That's 5 inches. And also, if you want to calculate the distance between the horizontal nail, process remains the same, but the only thing you need to do, so this is the simulation of a horizontal nail, and again, you can easily see two of them holds the top part from failing. So number of nails remains 2, capacity of nail remains the same, and I and V are the same. You can just simply replace QC in the formula. C is changing, reducing from 33.75 to 20.25, and definitely SC increases to 8.5. So you can replace the horizontal nails by, you can locate the horizontal nail in terms of distancing by a SC equal to 8.5 inches. Thank you. Solve more problem transfer shear in next videos.